For the invitation and also for the introduction. So I guess I should have my laser pointer here. Can you see the laser pointer?
Yes.
Yeah, okay. Yeah, so thank you very much for the invitation. And I am going to talk to you a little bit about seismic structures in the core-mantle boundary region. It's basically the core-mantle boundary region is a region that we can't easily go to. It's here between the outer core, the liquid outer core, and the mantle. And there is this region called D double prime, which I've been working on since my master's thesis with Michael Weber. The core-mantle boundary is basically separating the slowly convecting mantle and the fast convecting core. So there is an interaction through heat, mass, and momentum, obviously. And what we can see is that we have here the slowly convecting mantle, and then here the fast convecting core. Here's the CMB. And if we have on one side the dynamics of the mantle, this is just a figure from Bernhard Schubert, then on the other side the mineralogy of the mantle, then together they will form structures near the core-mantle boundary. And what you can see here is the large, low seismic velocity province, LLSVP, that are basically two big regions of reduced velocity, mostly in S waves, but also in P waves. Then we have ultra-low velocity zones here. These are very small regions. I'll come back to those later. We have slabs that may reach the core-mantle boundary, and we may have the origin of mantle plumes here. And on top of that, we have lots of small-scale scattering. So we have structure above the core-mantle boundary, but we might also have some structures below the core-mantle boundary, such as a stratified layer or a core rigidity zone. So we have these structures, and these structures sit at the core-mantle boundary. We have a different heat flow through the core-mantle boundary, depending on which structure we have above and possibly also below. And together, these structures may influence the magnetic field. And this is the topic of the Deep Dun consortium grant that we've got just recently funded, where we're actually looking at how does the mantle structure influence the magnetic field, the core magnetic field, and possibly vice versa. So there's more to come on that. So going back to the first slide, one of the things is that if we study different regions in the Earth in isolation, such as just the mantle or just the core, then we may actually get an incomplete picture. So what is important is that we know the processes and the structures of on both sides of the core-mantle boundary, because they do interact and they also influence what we see. And of course, if you look at one discipline, and I will show more of that, is that there are discrepancies. For example, in looking at just one seismic structure, you see there are discrepancies in there. And the question is, where are they coming from? Are they coming from because things are really different? Or is it just the interpretation? Or is it the resolution? And we don't really know. But what is important is that we would like to know how we can resolve those discrepancies and therefore get a good picture of the inner Earth, or maybe later the planets, who knows. Just taking a step backwards and looking at this again, so we have the Earth dynamics, as I just showed, and then we have the Earth mineralogy, and together they form seismic structures. And then seismologists go and interrogate those seismic structures with travel times, amplitudes, polarities, waveforms, and frequency content. And then we get the physical parameters of those seismic structures. And then those physical parameters we go and interpret in terms of dynamics and mineralogy. But it's an interpretation. We have to be aware of that it is really an interpretation. And our question is, or should always be, how unique are those interpretations? Does the choice of the waves, does the choice of the method affect our interpretation? And are there possibly influences from other structures in the Earth? So, for example, if you want to look at the core, your wave has to go through the mantle. Does that influence both the measurements and also the interpretation that we have. And it's a bit like this blind man and the elephant, where you have here all these blind men with the blindfolds, and each one is touching a different part of the elephant. And then the one here at the trunk says it's a tree, and or sorry, at the foot. And the other one on the side says it's a wall. And then this guy here says it's a spear when he touches the tooth. So each one of them interprets what they feel in terms of what they think could be best. But they don't see the entire picture. And I think that's what maybe happens to us when we look at the inside of the Earth, right? So we see something, we interpret it, but is it really the best interpretation? And I think a little bit of this talk will go towards what we actually know and maybe ways forward of how we can look at the interior of planets and Earth in more detail. But first, because I think not everyone is a seismologist here, I've seen a few non-seismologist names there. I would like to show some seismic waves that we're using. They will come back later, so a little introduction to those. The first one are the body waves. So we have P and S waves that travel through the Earth in some way. They may or may not be reflected at structures, or they may go through structures. And so if they reflect here, then we have an additional seismic wave from this D double prime region here, for example, that we can record at the surface. Body waves are also used in tomography. Tomography is usually done for planetary interiors, or especially the Earth mantle. And you have waves that travel in all directions through the Earth with crossing paths if possible. And then we do an inversion to find regions of low seismic velocity, such as these red regions here, or high seismic velocity as these blue regions here. And then we can go and interpret those in terms of hot material, possibly uprising, because hot is lighter, it rises, or cold and sinking material, because cold material is usually faster than normal material. So we have these body waves that can be used, S waves, P waves, and also PP waves, and so on. Another wave that or another observable we have are normal modes. So we use the entire recording, and then they're normal modes, and they're sensitive to different parts of the Earth. And especially looking at the core-mantle boundary region, there are some normal modes, they're called the Stoney modes, and they are especially sensitive to the core-mantle boundary, both above and below. And then people use these to test, for example, the large low shear velocity provinces and other regions. So I'll come back to those later as well. So when we have body waves, as I said before, we measure travel times, we measure amplitudes of seismic waves, but we also measure things like polarities and waveforms. So travel times can give us an idea about either the depth of a reflector, for example, or what kind of material the wave travels through. The amplitude can give us an idea about the velocity contrast across a reflector, for example. The polarity and the waveform can give us also an idea about the change of velocity and density across a reflector, if we look at a reflection. But complicated waveforms could be an indication for, say, layering or some sort of layered material. The frequency content isn't used that often yet, but it can tell us something about the structure of the size of the structure that we're looking at. Okay, so going back to our structures in the Earth, there's lots of different ones. There is these LLSVPs, large low seismic velocity provinces, or sometimes called large low velocity provinces. There's deep subduction, there's possibly the base of plumes, there's CMB topography, there's the D double prime reflector or reflectors, there's anisotropy, and there's stratified layers at the top of the outer core. And there's also small scale structure, ultra low velocity zones, core rigidity zones, or scattering. And I will look at these four red ones here: LLSVPs, D double prime, ULVZ, and scattering. So starting with the large low seismic velocity provinces, as LLSVPs. In many tomographic models, we see these two regions of large, two large regions of reduced S and P wave velocity. One is sitting under the Pacific and the other one is sitting under Africa. This is the model by French and Romanovitz, but it can be seen in almost every tomographic model of the Earth mantle that we have. So Lekic and Cotta and co-authors, they came up with this idea of stacking tomographic models. That's the so-called vote maps. And where all these models, so they used 5 different models where they all show slow velocities. They're colored. So if just one shows slow velocities, then it's this darkish blue. And then if 3 models agree with the low velocities, then it's yellow. And if all 5 agree, then it's red. And you can see there's these really big blobs of low velocities here under the Pacific and under Africa. And there's this small one that's called the Perm anomaly. If we look at those large low shear velocity or seismic velocity provinces, then you can see here for the S waves, this is now a vote map with 18 models. And you can see that for S waves, they agree really well. So obviously, most models show very similar pictures. But if you look at P waves, it doesn't look as nice anymore. First of all, okay, there is something here that seems to look a little bit like the one for the S waves here. But this velocity anomaly here under the Pacific looks different for P waves and for S waves. So here we have the elephant because maybe we just look at 2 different things here. Or maybe it's an effect of resolution or an effect of a selection of seismic waves. So what can we do to study these LLSVPs apart from looking at tomography? We can use waves that directly travel through this LLSVP. So if we have here a seismic event, and then the waves travel away from the event, and if we measure them here and there is nothing in between, then they will all arrive at the predicted arrival time. However, if we have something like a low velocity region in here, the waves that travel directly through it, they will be delayed. And the waves that travel along the edges of it, they will have a change in waveform. So they will have a broadened waveform because both the one that travels through the LLSVP and the one that travels alongside it, they will interfere and will change the waveform. And if you look at data, so this is from Ni et al., this is outside the LLSVP, then here you have a waveform change, and then you're inside the LLSVP. So that is one way of doing this. And another one, so here again is the travel time changes, but in this case from waves that travel through the Earth's core. Or you can look at amplitudes, and you see a change in amplitude as well, possibly due to focusing and defocusing effects. You can also look at reflections of the sides and other things. There's other ways of studying those LLSVPs. One of those is using so-called tidal tomography, as done by Harriet Lau, for example. So she's used GPS measurements, and then she tried to fit the interior of Earth with dense material, which is like these LLSVPs here. They are also dense in her models. But if you look at these Stoney modes that I showed earlier, Paula Kollemeyer shows that the observed splitting of these Stoney modes here are better fit with a light LLSVP than with a dense LLSVP. So the tidal tomography says it's more dense, whereas the normal modes say it's less dense. And then if you use mineralogical modeling to look at the observed seismic velocities, most people then use well, the low seismic velocity, and they come up with a density that is also higher than predicted, for example, by Kollemeyer. So just looking at the properties of these LLSVPs, the velocity is fairly consistent. So we have a drop in seismic S-wave velocity of 2% and a drop of P-wave velocity, but only 0.5%. So the S-wave velocity drops more than the P-wave velocity. And that's, of course, interesting, but it can probably be explained with mineralogy. There is also an anti-correlation of the bulk sound speed V phi and Vs, which indicates that we have some compositional heterogeneity in there. Okay, so velocity is not that difficult, but the density from normal modes, polar colomyosis, they're light LLSVPs. Perhaps the dense space from mineralogical modeling should be a density increase. From tidal tomography, as I showed earlier, Lau et al., they say it's a density increase, at least at the bottom of the LLSVP. So the bottom is the lowest 300 kilometers. And gravity observations by Wolfgang Swillus is a density increase. Okay, so there is, the elephant again, because we have lots of discrepancies here. What we do know is that we have chemically distinct and probably slightly negatively or neutrally buoyant thermochemical piles. But we can look in more detail at the LLSVPs. For example, we can look at the edges or the tops, because there have been publications that they have sharp edges, flat tops. And if you look at where these LLSVPs have been observed, here are lots of different studies from the paper by Ganero 2016, where he summarized everything that was known by that time about these LLSVPs. And you can see that, okay, for the Pacific, the outlines are sort of similar, but if you look under the Atlantic, these edges of the LLSVP, they're completely different, right? So the question here again is it different waves? Is it different resolution? Or what are we actually looking at? There are some recent reviews, Ganero 2016, McNamara 2019, and Kohlemeier in 2021, that give a really good overview over these. But if we then compare P wave and S wave results, they again show something different, right? So here, these are S wave contours for model SP12 RTS, and here's for the P waves. And again, you see these are totally different, very similar to what I showed before with the vote maps. But now these are the real tomography models without vote maps. So if we really want to know what's inside these LLSVPs, we need to have P wave and S wave observations together. And if possible, density as well. And then we can say something about what kind of structure, what kind of minerals we have that make up these LLSVPs. But also, these LLSVPs, as shown here as big blobs, again, this is the paper by Ed Ganero, these LLSVPs are these big blobs in seismic tomography. But they could be due to either a collection of plumes, a dome or a super plume, a stable pile at the bottom of the mantle, or some metastable pile that sort of moves up and down with maybe plumes coming from the sides. But if you look at those with seismic data and you apply something called a tomography filter, so basically look at what would tomography give us if you had these kind of different pictures here, then you would basically see the same thing. So you can't really resolve it at the moment. We might have to go to higher frequency waves to look at that in more detail. And then recently there was a publication by Anna Vai and Barbara Romanowitz that said that this LLSVP here could be really, that's the Pacific, could be really a collection of lots of different plumes as sort of indicated in these contour lines here. So the idea that it's not a stable super plume or dome seems to go more into the direction it's a collection of plumes, and that seems to show some sort of a coherent structure when you look through tomography. But is there a way of distinguishing between those different possibilities? And there might be one way of doing this, and this is if you look at the core-mantle boundary topography. Because if you have seismic, if you have these plumes going up, then you would have to have this kind of uplifting of the CMB. Whereas if you have a light pile, it's sort of a small depression, and for a heavy pile, a big depression. I think I've seen Bernhard Steinberger here. He probably knows even more about this than I do. But one of the things that we could do is really look at the topography of the core-mantle boundary. But that would be nice if it worked, but every wave that we could use to look at the core-mantle boundary topography also has to go through the very heterogeneous mantle. And so it will be influenced by mantle structure already. So one thing we have to do is we have to try and unravel the effects of the mantle to get the effect of core-mantle boundary topography. And to make things even more difficult, these LLSVPs also may have an internal structure. So this here is in the Pacific. That's a publication by Ota and co-authors, also based on a publication by Ley and co-authors in 2006, where they find lots of different reflectors at the edge of this LLSVP. Maxime Balmer has predicted that there's a hot primordial material inside these LLSVPs. And my PhD student, Lina Schumacher, has found some internal reflections in the Pacific LLSVP as well. So apparently it's not quite that easy to really look at these LLSVPs seismically or through gravity measurements. And therefore we also have a lot of explanations for what it could be. So in the literature, you find everything from a thermal origin, so maybe several plumes, to a thermochemical origin that includes things like the magma ocean, dense melts, the basal mélange, a primordial material, some geochemical reservoirs, and lots of other things. And based on that, the mineralogy of the LLSVPs can be explained by a large range of compositions, as has been shown by Villela and co-authors in 2021. So for example, if we have a magma ocean, we might have a material enriched in iron and aluminium, low ferropericlase and high silica content, or if it's MORB, then it could be calcium perovskite, bridgemanite, or other phases. It could be enrichment of calcium perovskite. The problem is that MORB down there actually has high seismic velocities. At least that's what some recent studies show. So MORB is probably not a good explanation for a low velocity region, since it does seem to have high seismic velocities. If it's primitive material, it should be bridgemanite or bridgemanite enriched or iron enriched. So LLSVPs are still a big question, but there is something else close to these LLSVPs, and that's these ultra low velocity zones here, and possibly scattering. And the question is, how are they connected to these LLSVPs? And are ultra low velocity zones and scattering connected? So if you go back to a publication by Yu and Garnero, where they basically collected everything that was known about ultra low velocity zones, what they showed here is the outline of these LLSVPs and observations in red of ultra low velocity zones. No ultra low velocity zones found here in blue, and maybe in yellow. So ultra low velocity zones are really these small regions of extremely low S-wave velocity and extremely low P-wave velocity, and possibly increased density. And they're very small. And here's work by McNamara, where he showed that preferably on the sides of these large velocity anomaly, or like these large blobs here. He doesn't say anything about seismic velocity in this case, but there could be these regions of melt on the sides of these blobs here. If I look at this, there could be some sort of a correlation, but there could also be no correlation. I don't know. It's maybe we need more observations. So the question is, how can we detect ultra low velocity zones? Here's a few examples. One of those could be what has been used right in the beginning, these SP-diff-KS waves. That's waves, S waves that travel to the core-mantle boundary. Then they are guided inside the ultra-low velocity zone. And then they travel as a SKS wave further to the surface. The waveguide or the traveling along the core mantle boundary can happen on the source side or the receiver side, and to distinguish between those is kind of difficult. So that's this part here. The red thing is the red lines are the model without ultra-low velocity zones, and the black is the observations. And what you can see here is that the observations, this SP-diff-KS arrives later than predicted and with a larger amplitude, which is due to the waveguide effect. You can also use PKP waves to do that. And that's similar, only that these PKP waves, as shown here, when they travel along or through an ultra-low velocity zone, they arrive as precursors to PKP. So what you have is this PKP, the B diffracted wave, that has, again, a larger amplitude and arrives later than the prediction with the red lines. The other thing you can do is look at reflections of these ultra-low velocity zones that could arrive as precursors to PCP, for example, in this case. And the last one is scattering, if you find some sort of coherent scattering as precursors to PKPDF. So if we look at some of these observations, we can look at the properties for these ultra-low velocity zones, and that's from the publication by Schule, Yu, and Edgar Nero, where they showed, first of all, the size of these ultra-low velocity zones. There's lots of different sizes, so they could be, thickness is between, not really clear, to over 50 kilometers. The sizes are about 100 kilometers or more, or less even. And then the velocity contrast, so the P wave reduction in percent and the S wave reduction in percent can be anything from 1:1 to 3.1 and even higher than that. 9.1 I've seen in the literature as well. So that means the S wave is, in this case, 3 times more reduced than the P wave, 30% reduced, and the P wave is 10% reduced, for example. And these ultra velocity zones have been seen at the base of plumes, near the edge of piles, at the edge, and also underneath slabs. So again, we're not really clear what it is. There's a large variation in these properties. And the question again is it dependent on region, on data, on methods? Yeah, it's a good question. But the thing is that these are small scale structures. And there's another small scale structure that we know, and that's well, small scatterers, really. These small scale heterogeneity are found in all kinds of different regions of the Earth. And this is just a cartoon, but basically shows they could be anywhere. And this is a modeling by Brandenburg and co-authors, where they basically run a model here and with some traces, and then afterwards they find that these traces have distributed everywhere in the Earth's mantle. There are regions without, then there are regions with lots of tracers or scatterers, as we may want to call them. So scattering, if it's like small particles, say from subduction or so, crust, they could happen anywhere inside the Earth. The way we look at them, or we have looked at them in the beginning, mostly is by looking at precursors to the wave PKP. So the PKP, the F wave, travels through the Earth's outer and inner core. And if there are small-scale heterogeneities somewhere at the core-mantle boundary, these waves may be scattered and may arrive somewhere as a precursor to PKPDF. And here, these data are aligned on PKPDF, and there shouldn't be anything ahead of that. But we see there are some wiggles, and these are scattered waves from somewhere inside the mantle. Mancinelli and Shear showed that if these scatterers sit at the core-mantle boundary, then we would see them here at this white line on the left side. If they're sitting somewhere 600 kilometers above the mantle, they should not arrive later, not on this side, but only on this side here. And in 1,800 kilometers depth, they would only arrive here in this last part. So looking at the travel times of those precursors, we can say something about where in the mantle they might come from. And then especially for Christoph, I put in this figure from Christoph and Klaus Bataille from 2020, where they say that it's not only in front of PK-PDF here, but you can also see this here as postcursors. You can see this here in front of PKKP and as PKPAB precursors. So there's a lot of information in the seismic wave field that we haven't really tapped into, but that we could use to look at these scattering bodies. And if we start looking at them in different regions, so this is a collection of source-receiver combinations that I looked at once just to see if scattering is visible everywhere. And the thing is, yes, you see it in almost all of these source-receiver combinations here on the right, but with lots of different amplitudes. Here is very, very small. This is South America to Canaan, whereas Papua New Guinea to Cameroon is very, very large. And the same Vanuatu to Ethiopia, very large scattering, partly even larger than the PKP wave itself. So the question is, what does this mean? And these are all the observations that I have. So you see there's a huge range of amplitudes of these scatterers compared to PKP. And the question is, why is that? People have also seen this here. Mancinelli and co-workers have done this in 2016, where they also look, maybe there's a directional strength of scattering, so something like an anisotropic scattering, but it wasn't really that clear in his data set. And Lauren Watzek here, she also looked at the strength of these precursors, and you can see that it basically everything is there. Yeah, you can have anything. So we had some explanations for these PKP precursors in the past. So for example, scattering at slab remnants or scattering of the sides of LLSVPs, small inhomogeneities, whatever they may be, near the core-mantle boundary. So if you don't know what it is, you just call it inhomogeneity. It could be a caustic effect or a diffraction from the caustic. And that has already been postulated quite early in the 70s. It could be reflections from transition layers, or it could be core-mantle boundary topography. But again, core-mantle boundary topography is kind of difficult to test if you have scattering above it. So the question now is, are these scatterers and these ultra-low velocity zones, are they possibly related? And this is a publication by Xiaolong Ma. He was in Münster as a postdoc, and he looked at scattering in a huge data set again. And he found in many places where these gray dots are shown, something that he called coherent scattering. That's this thing here, where you can really follow it. And if you stack the slowness versus time in a vespergram, you can actually see an arrival here that comes from this coherent precursor. But there's other regions where you don't have that. So these are just incoherent scattering. You wouldn't see a coherent wave in there. So what he tried is he tried to model these observations. And for example, a model with a 1,000 kilometer thick model with just a random scattering properties inside would create something that looks similar to this kind of scattering here. This is an observation, this is the model. But he can also, when he puts in a small low velocity anomaly, that doesn't even, it's not even minus 30 or minus 10%. You get these coherent precursors that come and go. So there's some interference patterns here, which is similar to what we see in the data. So this coherent precursor here sometimes is visible and sometimes is not visible. It's similar to these synthetics here. So there might be just, they might be sitting together, these scatterers and the ultra low velocity zones, or maybe very small scatterers, when they accumulate, form an ultra low velocity zone. So what I showed so far is that ultra low velocity zones and scattering may be related. These LLSVPs and ultra low velocity zones may be related, or at least they coexist. And now the question is the scattering and this the double prime reflector, are they possibly also related? And so for Michael, I'm going back to my master's thesis. where we saw this reflection of the double prime. So you have the P wave here that arrives here, then you have the PCP wave reflecting off the core-mantle boundary, and then you have a reflection of this D double prime layer that's about 200 to 300 kilometers above the core-mantle boundary. And that reflection here will cause an additional wave between P and PCP. And if you look at the data, these are distance-dependent data aligned on P, then you can see this reflection of the double prime coming here with a different move out compared to P and also PCP. And to identify them even better, we do these Vespergrams. So here is shown the slowness over the travel time. So basically the angle of arrival or incidence angle at the array, or the apparent velocity. So if you have a very steep wave like PCP, then you have a low slowness. If you have a shallow wave, shallow traveling wave like P, you have a high slowness. And you can see here already that PDP arrives with an incident angle that is sort of between P and PCP, and that would identify the wave PDP here with a slowness that is between P and PCP, and a travel time that's also between P and PCP. So that's how we look at them and identify them. And these D double prime reflectors have been identified in many different regions, and actually in some cases 2 and even more reflectors have been observed. Here, for example, by Hutko under the Caribbean, here under Eurasia, and here in the Pacific itself. So there's lots of observations of the D double prime reflector. And if you look at those observations, here in green are the S wave D double prime reflections, in P, the P wave reflections in blue, and they are overlain on this VOTE map, and now with high seismic velocities, here for S waves and here for P waves. Again, what you can see is that the S waves for the VOTE map agree well, whereas the P waves don't. And you can see that the D double prime reflection observations are mostly in regions of high seismic velocities in tomographic models. We also have regions where we don't see any evidence for D double prime reflectors despite extremely good data quality. And they are in regions where we do see reflections as well. So why is that? Just showing you some examples here. So this is data recorded at the German Regional Seismic Network. Here you see the P wave, the PCP wave, and then here PDP with an amplitude that I would call sort of normal, and which corresponds to a probably 1% velocity increase across D double prime. Here you see a very, very large amplitude. Here you don't see anything between PCP and P. So there doesn't seem to be a D double prime reflection. And here for an S wave example, there is something, again, SDS, S and SCS with a normal amplitude, as I would call it. So the amplitudes vary strongly, but also the polarities vary. So if you look at this example here, down here, the bottom one, you see, if you look at the polarity, the PCP polarity is downswing, upswing, and PDP is downswing, upswing. So it's the same polarity, and I mark this with a plus. If you look at S, it's the same thing, upswing, downswing, same polarity, marked with a plus. If I go up here, you have the S wave, SCS and SDS, both an upswing, so same polarity. But if you look at this one here, the PDP is an upswing, downswing, and PCP is a downswing, upswing. So that's the opposite polarity. And we are outside this area where PDP shows the Hilbert transform. So that's for Michael, if you ask that question later. So this should still be the same waveform. And in this case, it's opposite polarity, so marked with a minus. Up until 2004, there were different explanations for these D double prime reflectors. So there was the reflection of a subduction zone, or the reflection of a thermochemical layering, for example, but also scattering, or maybe a change in anisotropy or anisotropy itself. And then in 2004, post-perovskite was discovered. So that's a phase transition from bridgemanite, or as it used to be called, perovskite, to its high pressure polymorph post-perovskite. So once that was discovered by several groups more or less at the same time, we started re-evaluating our seismic observations and whether they could be explained by post-perovskite. And indeed, post-perovskite can really explain a lot of things. It can explain topography of the D double prime layer. It can explain anisotropy and all kinds of other things. So it was a good thing. And in addition, it can also explain these observations of a opposite polarity, PDP, as I just showed 3 slides ago, while the S wave has the same polarity. Because of a reduced bulk modulus for post-perovskite, the P wave velocity drops while the S wave velocity increases. And that was a nice thing that, you know, the P wave velocity can reduce while the S wave velocity can increase. But again, then we have these cases here where the P wave velocity increases as the S wave velocity increases. So post-perovskite cannot explain this. Now we can still explain this using anisotropy, an alignment of post-perovskite, for example, or we can explain it with a stronger change in Vs than Vp, but I'm not going to go into this now. We tested a different thing. Frank Scheerbaum in 1997 already published something and said that because the double prime reflections were so variable, maybe they were reflections of fairly large scale scatterers. So what my PhD student Vanessa Hima did in her PhD, she did modeling of scattering, and this is very small scale scattering, so not the one that was predicted by Scheerbaum and co-authors, but much smaller scale, more like ultra low velocity zone and smaller scattering. And she puts a layer of scattering into the D double prime region with or without tapers, and then she looks at whether this creates both PKP precursors and whether it can also do something like a PDP wave. So these are observations of a PDP reflection, as we would call it usually. And in Vanessa's work, you find here a PDP, or something that we would call a PDP reflection, even though there is no reflector in there. There's just a scattering medium in there. And the scattering medium can create both the arrivals and the variability in arrivals and amplitudes of these PDP waves, as well as sometimes the polarity variations of PDP. And that's interesting. We haven't done this, we haven't looked at this for S waves yet, but that would be a really interesting way to do. So obviously, even the D double prime reflector can be connected to these scattering occurrences in the Earth's mantle. So just to do a first conclusion, the core-mantle boundary is or seems to be very heterogeneous. We have structures on many length scales, but we look at them with different methods and different data, different frequencies. So the question is, do we have this heterogeneity because we have lots of different methods? And it would be really interesting to look at one region with lots of different methods and see what we can get out and whether it's maybe the same thing. I don't know. But based on these different length scales, we have lots of different origins of these structures. Mineralogical and dynamical origins are discussed. We have some that match well, but others we need assumptions, or we need to know things that we currently don't know. And also the interpretations are very difficult or different. So we can interpret our structures in terms of mantle flow, in terms of mineralogy, but we have a lot of ambiguity. So it's not really clear what we have in there yet. Okay, but going on and just looking at, it's another 2 slides only, looking at the effects of the CMB structure on the magnetic field, because now I said there's lots of these structures. So but they have an effect, as I said right in the beginning, on the core convection. So if you look at the field map here, this is a publication by Gubbins and co-workers from 2008. So if you have the field map of the magnetic field at the core-mantle boundary, you see these blobs here of fairly stable magnetic fluxes or flux patches. And these seem to be stable over long periods of time. And if you produce a boundary model with, a core model with the boundary condition taken from tomography models, then you get some model that looks fairly similar to this mantle model, the core model that you have here in the field map. So it will be very interesting to see how these structures in the Earth's mantle influence the convection in the core. And that's the Deep Dun project that we're just starting, hopefully. So everyone up there in Potsdam and Berlin can talk to Monika, Sergey, and Christoph is also in there, lots of other people. So talk to these people that are connected to Deep Dun to see something else that comes from this collaborative effort. But if we have these mantle structures, then they may also influence the core convection in, for example, making this stratified layer that I showed in the beginning. But if you have a stratified layer, that in turn might again affect the magnetic field that we see at the surface of the Earth. So the mantle may affect the core convection, and then the structure in the core may again change the core convection, or at least the picture that we see. So to complete my conclusions, the influences on the magnetic field, there are some influences very likely, and hopefully we're going to find out with Deep Dun which effects they are. But just to give you a few ways forward, so one of the things is, don't just rely on one method or one data set, but look at the entire structure, or in this case, the entire elephant, to see that there is really an elephant and not a rope, a tree, or a wall. So we need to resolve the discrepancies. And when we have a discrepancy, we should not publish it, but we should publish it and start trying to find out what it actually means that there's a discrepancy. We should combine different seismic wave and techniques. We should use all the information that's available from seismic methods or waves, not only travel times, but amplitudes, polarities, waveforms, anything that we can see. We should be multidisciplinary, or we should approach this multidisciplinarily. And we should visit, or you should visit SETI in 2024 on the somewhere in the US. The final destination will still be decided soon. And you should watch results from Deep Dun. And there will be in 2023, in July, there is the IUGG in Berlin. So you're all very close. And there will be a SETI sponsored session, a union session, everything about deep Earth. So I hope to see you all there. And that's the end of my talk. Thank you.